sequential search. What we're going to be focusing on, since this is sort of a semi-intro class, is searching through an array. Okay, that's going to be the thing that our database, so to speak. All of these things would also apply to an array list. Okay, from your reading, what did y'all read about the linear or the sequential search?
The slowest one.
Okay, it's extremely slow. Oh, it's just the worst. Yeah. Okay. Why is it so slow?
Because it goes like one by one.
Yeah.
It's each string.
And it checks everything.
Checks everything. Yeah.
So
All
can
right.
it be more accurate technically
Even
too?
if it finds what it's looking for.
Not necessarily. That you can be a little smart about that, and if you find what you're looking for, you can stop. This is a version of the linear search or the sequential search that's going to return a Boolean, a true or false value, based on whether or not what it's looking for is in the array. Okay, so we can imagine that our array A 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 has, the values 5, 10, 15, 20, 30, 40, 60, 70, 80, 100. So that's our array. I've got them all sorted in this case, but it actually doesn't have to be sorted for you to do a linear search. And then you have your key. That's the value that we're looking for. So let's say we are looking for 30. With this algorithm with this method, it says, okay, we're going to go through the array, int I equals 0, I less than the length, I plus plus. If a sub I equals key, so we're going to look at each one of these. If it equals the key, then return true. And as soon as you do, get out of there. If we go all the way through here and we can't find the key that we're looking for, then return false. So it's going to say, does that match the key, or does this value match the key? Nope. What about this one? Nope. 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 Yep. Return true. If, say, you're looking for a key value of 199, nope, 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 okay, return false. And you can see you've got to go all the way through that. That's not really very efficient at all. This right here is another form of linear search, but we are returning an int, and what we're returning is the index of where that key happens to be. So you can see once again we have a for loop. We're walking through the array starting at 0, going all the way to the end. And if a sub I equals the key, then we're going to return I, namely we're going to return the index. So for instance, if our key was 30, nope, 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 yes, we're going to return 4. Okay, the index there. If you go all the way through, can't find the key that you're looking for, then you're going to return -1. All right, -1 is sort of like that, ever-present, it's not here value, because if you notice with the index, you're never going to have an index of -1. The index always starts with 0 and counts down. Okay? So that's for an integer array. It's possible for you to do a linear or a sequential search on strings, where all of these are strings. I'm not going to write down 10 different strings, but you can see once again we've got a for loop. The difference is, instead of saying equals equals, we're saying if a sub I dot equals the key, then return that index. We're using the dot equals method. You could also use the dot equals ignore case or whatever, because you can't use equals equals with strings. Here's that same linear search idea of looking through step by step by step by step, but utilizing an enhanced for loop. Okay? And you can see the difference here. This one is, once again, we're reverting back to Boolean given either a true or a false value, and we're just saying for each string str in the array A, if str equals key, return true, otherwise false. You can't send back the index with the enhanced for loop, because if you remember, the enhanced for loop doesn't have indices, it doesn't keep track. You have to manually do it yourself, but in that case, you might as well use regular old for loop. This is a little bit big picture here, but one thing I wanted you to see by having all these different Java code variations, all of those are different ways of implementing what we call the linear search algorithm. Okay, the word algorithm is more of an abstract term that says, this is the step-by-step process to solve it. Okay, to solve this particular problem. If you have an algorithm, you can implement it in Java. Okay, in this case, you've got a couple different ways of implementing with Java, different ways of writing the code. You could write that linear search algorithm. You could implement it in C or C++. You can implement it in Swift or Python. Okay, the algorithm itself is independent from the language. Okay, the algorithm is the idea of how you solve that. So we're talking about linear search. In a little bit, we're going to talk about binary search. Java doesn't have the corner market on binary search. Any programming language could implement these algorithms. All right, you already said why this is terrible, right? Why do we not like linear search?
Slow.
It's slow. You've got to check every single one. Now, what's best case scenario?
It's first one.
It's first one. What is worst case scenario?
It's last.
Or last one, or
Not there.
not in there at all, because you've got to go all the way through it. Okay? On average, some are going to be here, some are going to be down here, some are going to be in the middle. On average, it's going to take about half the amount of time. You're going to have to search about half the array. Okay? Sometimes we're concerned with the best and the worst. Sometimes we're concerned with the average. We'll think about the worst case scenario. So, yes.
Does this tie into, like, last year you played a video for your, like, AP computer science kids where had, like, these bars and, like, separate them? Is that what you're...
We're going to get there. Yes. Yep. That was sorting.
Bubble sort.
Yeah, and that was bubble sort that you saw, one of the first ones. We're going to do with that. Like I said, that's putting them in the right order.
Yeah.
This is searching for it.
Okay.
Okay. Sorting is after spring break.
Okay.
So keep that. But yes, you're the second one that mentioned that. Yeah, it's pretty cool. I love those visualizations. So if you think about it, if we were to plot the time that it takes, what does for this to run? What does the time depend on?
How many
Distance.
Yeah, it depends on how big this list is. Okay, so we could say it's the problem size. How big the array is. Okay, sometimes we'll give a letter for that. We'll say n. In this case, n is 10. Okay, we could have an array size of 100 or 1,000 or 10 million or whatever. But what we see is that the time that it takes is linear as it relates to the problem size, okay? Because as this problem size grows, the time grows. It's literally a y equals x function, okay? In fact, we could say f of x equals x. That's another reason why it's called linear. In computer science, when we're talking about the time cost, depending on the problem size, we don't use f of x, we use big O as a function of n. And that's literally what we say. This is the big O notation. So the big O of linear search is n. It has a big O of n. Or we say it's linear because this is a linear relationship. Linear relationships are not that great, okay? Because a lot of times your problem size could double, triple, multiply by a factor of 10. And if your problem size multiplies by a factor of 10, then your time is going to multiply by a factor of 10. You might say, that's no big deal, I'll just get a faster computer, okay? All right, you see how much is it going to cost you to buy a computer that's 10 times faster? Can you buy a computer that's 10 times faster?
Depends
Can you
on
buy
what
a
you start
20?
with.
Can you buy a
Depends on the
20?
original specs.
Can you buy a 20 gigahertz processor? I don't know. You guys are the ones that would know.
You can't go any faster than 5.5.
Might as well just make it fast from the start instead of trying to have a quick make up for it.
Yeah, absolutely. So yeah, this algorithm, even the fastest computers, it's still going to take forever.
Yeah.
Okay, and so what we, if it's quadratic? Oh my gosh, y'all know what quadratic graphs look like. Skyrocket. Cubic, exponential? No way. We need something that's a reverse exponential. A logarithm, yeah. We need something that's going to grow like this, where you go from 10 to 100, and this thing goes from 1 to 2. And it goes from 100 to 1,000, and this goes from 2 to 3. See what I'm saying? That's what we need. And if you can get logarithmic big O, a big O of log n, then you are dealing with something that's awesome, because your problem size can grow like crazy, and your time is only going to go up, by one, and then another one. And so that big O of, we would say, of log n is what binary search can do, and it's just unbelievably awesome. So let's talk about binary search. So those of you that did the reading, talk to me about binary search.
It's only useful in very specific circumstances.
Okay, and what is that specific circumstance?
Ascending or descending order.
Okay, that's yes, that is a caveat, that is a requirement, but it's not that special. I mean, it's not like, so you've got to have it sorted. Okay, they've got to be in order, either ascending or descending. And you're like, well, that's going to take forever, right? Well, that is a big problem of sorting them. But it's not an impossible problem, and it is, and we have lots of really different, interesting ways of sorting. Okay, so take my word for it. Sorting is not as hard as you might think. It's actually a really fun problem to think about. But yes, absolutely, they've got to be in order. Oh, good. I've already got a list here that's in order. Somebody else tell me what else about binary search? You know why it's called binary?
This goes by the numbers or ones and zeros instead of.
No, it
Not so much. Not so much that.
Like it divides the array into two,
Mm-hmm.
and then it continues until it gets to the correct element.
Yeah. Binary, because it's going to be two, it's going to cut the problem in half. Now, what you're saying, it solves as ones and zeros. Yes, that is correct. But so does pretty much almost any code that you're going to write with.
Right.
It's going to reduce to binary code. So this is more dealing with the fact that it's either, you can almost call it like, like the yes or no, search, like or above or below, or the high-low guessing game. Y'all ever play the high-low guessing game?
Mm-hmm.
Like I've got a number
We
between
have
1
a-
and 100.
We have a program.
Yeah, we have a program for that, right? Okay.
Mhm.
So I haven't played the high-low guessing game with me, and I'm going to play it in a dumb way, all right? So think of a number between 1 and 100.
Okay.
You got it?
Mm-hmm.
Okay, is it 1?
Yes.
Yes. But also no. Okay, you're out. Keen, think of a number between 1 and 100. You got it?
Yep.
Is it 1? Higher or low? Is your
Higher.
number higher?
Higher.
Higher. Okay, 2,
Higher.
3,
Higher.
4,
Higher.
5,
Higher.
6. Is it 6? Okay, all right. So, but see how that's kind of dumb, right? What's the smartest guess that I can make for my first guess?
50.
Yeah, 50, right? Because if I guess 50 and he tells me high or low, I've already eliminated half of the choices.
Right.
All right. Think of it like you are. We're pretend this is a dictionary. I get rid of all my dictionaries. Give it to the library. But pretend it's a dictionary. I'm looking for the word horse. Okay. And I don't have an index. And I don't have, kind of an awareness of where it's going to be. Okay. So, what's a very straightforward approach to finding the word horse?
H.
I can look for the H, okay, but I don't know where the H's are.
Search and have.
G.
Okay, so that's kind of what I'm looking for. So search in half, go right down the middle. All right, I found mouse. What am I gonna do?
Before.
It's
Yeah.
gonna be before that, okay? So since my left hand and my right hand, okay, are kind of like on either side here, I'm gonna put this hand right in the middle, okay? And now I'm dealing with this. only half the problem. So I'm gonna look at this. Cut this in half. Find the midpoint. Jackrabbit. Still
Okay,
before.
yeah,
So do the same thing. Put this hand right here at that midpoint. Now I'm just looking at these, right? Cut it in half again. Cat. Going the other way. So I'm gonna lift with this hand, put it right there at that midpoint. Now I'm just doing this. Do you see where I'm going with this? It's a divide and conquer technique. Yes,
So
Jay?
basically, like, is binary search, like, I'm trying to visualize it, like on that bubble, like, graph thing, is it like where you split it in half, and then you got, like, and then they kind of sort each other out, and then they throw them?
Not quite. It's similar to that. Actually, yes, where you're dividing and conquering. You know, you're dividing, and then you're only looking at this part. Then you're only looking at this part. Then you're only looking at this part. Then you're only looking here. So yeah, it's kind of like that. We're gonna do a visual here, so you'll be able to see how that works. Okay. Yep. Let's get going here. So, like Cameron said, to do a binary search, it's got to be sorted, either ascending or descending. We have ours in ascending. All right, and so there it is. This is one way that you could do a binary search in Java. You see, we've got our array of integers and the key that we're looking for. So I'll just kind of walk through the code and then we'll trace it. So you're going to have a left and a right. It's almost kind of like a high and a low. We kind of think of those like your hands. Okay, one's on the left, and the other one's on the right. And then as long as the left and the right are in the right position, where left is to the left of right, left is less than or equal to right, then you're good to go, and we're going to go in this while loop, okay? First thing we're going to do, find the midpoint, right there, nose right there, so to speak, okay? Then compare that midpoint with whatever your key is. If it's a match, hey, you're in luck, you found it, get out of here. Return the midpoint, return that index. Otherwise, if the midpoint is less than the key, then move your left up. Okay, in fact, you can move the left to the midpoint plus 1 because you know it's not at the midpoint. Otherwise, move your right to midpoint minus 1. So, like that. And you're still only dealing with half the problem. Okay? Loop back around. Is left less than right? Is left less than right? Yep, absolutely. So do this whole thing again. Find the midpoint, either move here, or find the midpoint and move here, depending on where it is. Then repeat, repeat, repeat. If you, in the process of doing this, you make it to the point where you don't find it, and actually the left and the right end up getting switched. In which case, you will no longer have left less than or equal to right, and you'll kick out of this loop, and then you'll return -1. And we're going to do each one of those cases. So, while I take attendance, I want you to copy down that integer array. All right, so we've got our array and our key value that we're looking for. I'll have a variable for left and a variable for right and a variable for midpoint. All right, and here we go. Let's go ahead and look for 30. Why not? So left equals 0. So if you have a pencil, it's really good for this part here. for right over here. Right equals the endpoint minus 1. So, so 9. All right, so if y'all answer me this will go a little bit faster here. Is left less than or equal to right?
What's that?
Yeah, okay, sorry. Yeah, just yes or no. Like, is it less than or equal to?
Yes.
Yes, it is. Okay, so we're going into the loop. Midpoint equals left plus right over 2. So 0 plus 9, 9 divided by 2, 4.5. But we're doing integer division, so 4. Well, okay. Oh my gosh. Okay, this is going to be fast. All right. So then, is the value at the midpoint equal to the key?
Yes.
Yes.
It is. First try. Great. So let's return that. So return midpoint. So return 4. Okay.
Best case scenario.
Yeah. That's great. Okay, so let's try another one.
5.
Let's try 20.
Yep.
So initial values, we're going to have 0, 9, and 4. Is left less than or equal to right? Yes, it is. So the midpoint, we've got it, it's 4. Now, is the value at the midpoint equal to the key? No, it's not. 30 versus 20. Is the value at the midpoint less than the key? Is 30 less than 20? No. So that means we're going to this else branch. Right equals midpoint minus 1. So right is going to go here, midpoint minus 1. Notice, now we've just all of a sudden got the problem in half. Because now we're only going to be looking between left and right, between these two. Okay? And I'll update my right value to be 3. Okay? Midpoint, technically when we get here and loop back around, midpoint resets, but I'm just going to leave it over there. So, question, is left less than or equal to right? Yep, going into the loop. Midpoint, left plus right over 2. 0 plus 3 is 3 divided by 2, 1.5. Integer math puts it as 1. So, midpoint's there. Is the value at the midpoint equal to the key? Nope. Is the value at the midpoint less than the key?
Yes.
Yeah, it is. 10 is less 20. So, left equals midpoint plus 1. So left is midpoint plus 1. So left is going to be right here. So, left is now 2. So ignoring that midpoint, since that's kind of out, look at we're only looking at these two spots right here. It's got to be one or the other, or neither. Loop back around. Is left less than or equal to right?
Yes.
It is. So we're going in. Midpoint is left plus right over 2. 2 plus 3 is 5. Divided by 2 is 2.5. So 2. So midpoint is 2. Next up, is the value at the midpoint equal to the key? Nope. Is the value at the midpoint less than the key?
Yep.
Yes, it is. So, therefore, left equals midpoint plus 1. So, right is equal to this one. Left is now also equal to 3. Loop back around. Is the left less than or equal to the right? Yep, they're equal. They're both pointing at the same one. Okay, midpoint, left plus right over 2. So 3 plus 3 is 6. Divided by 2 is 3. Is the value at the midpoint equal to the key?
Yes.
It is. Hooray. Return the midpoint. Return 3. We found it. That was worst case?
I think so.
Possibly.
Well, worst case would be it not being in sequence.
That's true. Okay. Well, in that case, you don't have any guarantees that if you cut it in half, you're going to have the problem. Okay. Yeah, that did take pretty much all. It seems like is the maximum amount of times for this data set. Okay. We're going to do another one. Any questions so far, though? Y'all kind of see how it's working? It's just logical. What you do actually, you do this, and then you do that. Okay. We've done what we found on the first time. We've done where it took us several iterations. I would like for us to look for a key that's not in there. Okay? So, what do y'all, give me a key that's not in there.
-1.
-1? Okay. We might be able to tell that real quick though, because we can just say if it's less than this value, or if it's more than that, we can do real quick to see if it's even in the range. You know what I mean? And we can do that in constant time. So I like that thought, but I'd rather try to find one that's not inside the list, but is within the range.
50.
50. Okay, yeah, it makes sense. We've got a bunch of numbers. Let's see if 50's in there. This first part's pretty easy. Left starts off at 0. Right starts off at 9. And of course, the midpoint, 0 plus 9 is 9 divided by 2, 4.5, so it's going to start off at 4. Okay. Is the value at the midpoint equal to the key?
No.
Nope, 30 is not equal to 50. Is the value at the midpoint less than the key?
Yes.
Yeah, 30 is less than 50. Okay. So, therefore, left equals midpoint plus 1. Left equals 5. Back to the top of the loop. Is the left less than or equal to the right?
Yes.
Yep, it is. 5 less than 9. So, midpoint, let's update the midpoint.
6,
5 plus 9 is 14. Divided by 2, I think it should be 7.
7, sorry.
That's fine. So, 7. Alright. We're so close, but binary search doesn't know if you're really close. It's just gonna blindly cut in half each time, which is not a bad way. It works too. So check the midpoint. Is the value at the midpoint equal to the key?
No.
Nope. Is the value at the midpoint less than the key?
No.
No, it's actually greater than the key. So that means we're going to do this one. Right equals midpoint minus 1. So right is going to equal 6. Flip back around. Is the left less than or equal to the right? Yep, everything's still in good shape. Okay, going in, update the midpoint. 5 plus 6 is 11. Divided by 2, 5.5. Integer math, 5. Is the value at the midpoint equal to the key? 40 and 50? Nope. Is the value at the midpoint less than the key? Yeah, it is.
Oh, yeah.
So, set left equal to midpoint plus 1. So, left is now equal to 6. Let's go up around. Left is left less than or equal to right? Yeah, they're equal. Update the midpoint. 6 plus 6 is 12, divided by 2, 6. Alright, so we're all here. Left, right, midpoint. This has got to be it. Is the value at the midpoint equal to the key?
Really just loop?
Nope.
We'll find out. Nope, it's not. Is the value at the midpoint less than the key? Nope, value at the midpoint is more. So right equals midpoint minus 1. So right is going to equal here.
And now it won't be this.
Oh, yeah, that's right. Okay. Because they both passed each other.
Yep. Now we go up and we ask that question, is left less than or equal to right?
No.
No, okay, so yeah. And you can't see that unless you trace it. You just got to do it. That's why we go through this activity every year, because it's essential. So, all right, it's not. So kick out of that while loop completely, and we're going to return -1. And that's gonna happen every time. You're gonna keep the point that you zero in on. It's either gonna be that particular point, or it's not, and it's going to be high, or that one that you're looking at is going to be higher or lower. And if it's higher or lower, then left or right is going to move accordingly. It'll end up moving past it, in which case the while will catch it. Okay? So that's a very straightforward, step-by-step way of looking through binary search. Now, something I added here last night was the recursive binary search algorithm. You might say, ooh, that sounds interesting. Because if you think about it, this algorithm, it has very much of a recursive feel to it, right?
Yeah.
You're having the problem, cut it in half, and I'll do the same thing again. Cut it in half, do the same thing. Cut it in half, do the same thing again. So I have a very short one-line method right here called binary search, where you have an integer array and a key, and then I'm calling this index of method. Now, I'd love to take credit for this, but this is not me at all. This is, I took it from another book. So anyway, so this method accepts as its parameters the integer array, the key that you're looking for, a low, and a high, which that's really all that you need. If you look, this says if low is greater than high, which means that you flip-flopped, return -1, we're done. Set the midpoint equal to low plus high minus low over 2. Okay, so it's basically the average. Okay, wherever the low is plus the distance between them. Anyway, if the key is less than the midpoint, so that means you're down here, return index of, which means to call this whole method again. The array is the same, the key is the same, the low is the same, but instead of the high, call mid -1. So that's sort of like your loop back around calling itself. Otherwise, if key is bigger than mid, return the index of a is the same, key is the same, but then have that mid +1 for your low, and the high stays the same, so you're doing that other part. Otherwise, return mid because you found it. It's either your key is either too high or too low, or you found it. So that's kind of a neat way of applying it recursively. Okay, just another way of showing that you can implement this. The code is still implementing the binary search. Okay, tomorrow what we're going to do, we'll look at the analysis, and we'll actually implement this for some searches.
Hi out there.